This is Unit 5, video number 9, empirical formula. Okay, empirical formula is the lowest ratio of atoms in a compound. It's often all we can get from experimental evidence. So real molecules are going to be some multiple of the empirical formula. For ionic compounds, they're always empirical formulas. So empirical formula, being the lowest ratio, if we have a compound like octane, which is C8H18, then the empirical evidence is going to tell us that the compound is, and we're going to divide out the greatest common factor, which is 2. So we're going to have C4H9. This is the empirical formula. This is what we call the molecular formula. The real molecule is C8H18. But empirical evidence is going to give us C4H9. And then we're going to have something else that tells us what this value is. Okay? Some other examples, if I had N2O4 dinitrogen tetroxide, then the empirical formula is going to be NO2. Okay, one more, classic compound, glucose, C6H12O6. Greatest common factor here is 6, so we're going to have CH2O. This is a very common biological and empirical formula. So empirical formula is the lowest ratio of atoms in a compound. Now, we're going to take percentages. We did percent mass, you understand percent mass. We're going to take those percentages, and that's what empirical experimental evidence would give us. We could say, okay, 60% of this compound is iron, or 20% is silver, that kind of thing. So we're going to take some percentages and create the empirical formula. First one we're going to do is a mixture of phosphorus and fluorine. So what we have is 35.2. So we're going to determine the, and I'm going to use EF. If we have 35.2% phosphorus and 64.8% fluorine. So that's what we're going to do. We're going to take 35.2% phosphorus, 64.8% fluorine, and determine the empirical formula. What you're going to do is you're going to assume a 100-gram sample. If we have a 100-gram sample, then 35.2 grams of that 100 grams is phosphorus, and 64.8 grams is fluorine. So let's take 35.2 grams, which is phosphorus, and right underneath it we'll put 64.8 grams, which is fluorine. Compounds are in atom ratios or mole ratios. So we're going to figure out the number of moles. Phosphorus's molar mass on the periodic table is 30.97. So we'll get that right off the periodic table. I'll go ahead and put fluorine down here. 1 mole of fluorine is 19 grams. So now we're going to have the moles of phosphorus and fluorine. The moles of phosphorus is 1.14. The moles of fluorine is 3.41. So this tells us that our compound is P1.14F3.41. But that's not very useful. And John Dalton told us that compounds are given composed of atoms in small whole number ratios. So we're going to determine this as a small whole number ratio. How are we going to do that? We're going to get rid of these fractions. So we're going to divide by the smallest value. Now obviously something's going to be 1, and in this case the phosphorus. If we divide that out, you're going to get 2.99999, which is 3. So our compound actually is PF3. Okay, so that's empirical formula. Take your percentages. If you're given grams, just calculate with the grams. But if you're given percentages, assume a 100-gram sample. That will bring your percentages into grams and then convert them into moles. Now we do one more example, and this is going to be a carbon-hydrogen compound. Okay, so we've got 83 points, we want to determine, I should have left this up. .6% carbon and 16.4% hydrogen. So there's our two. We've got 83.6% carbon and 16.4% hydrogen. Obviously, if only one percentage was given, it's a binary compound too, then you just subtract from 100 and get the other percentage. So it shouldn't be, you might see problems where only one's given. That's fine. Again, we're going to assume 100 gram sample, not 10 grams, 100 grams. If we have a 100 gram sample of this compound, 83.6 grams will be carbon. So we have 83.6 grams of carbon. We have 16.4 grams of hydrogen. I'm going to convert these to moles because our empirical formula and molecular formula are in moles, not in grams. So don't divide through or anything here. Convert these into moles. 12.01 grams, 1 mole. 1.01 grams, 1 mole. Punch that into our calculator. We're going to get 6.96 moles of carbon. We're going to get 16.2 moles of hydrogen. So we have 6.96 moles of carbon, 16.2 moles of hydrogen. They're going to go in. What we're going to do now, again, we can write it. We can write C 6.96, H 16.2, but this is not the way we represent compounds. We represent them in small whole number ratios. That's what John Dalton told us, and that's the way we universally do it throughout chemistry. So we're going to divide by the smallest value. When I do the carbon to 1, 6.96. Now when I do this, you can see that's about 7. 16 divided by 7 is not 2. You're not going to round this up. Leave the fraction. That's going to come out to 2.33. You'd say, well, what is that? Then I have C1H2.33. Well, what we're going to do here is get rid of this fraction. 0.333, you know, is 1/3. So I can get rid of the fraction by multiplying both of these by the denominator there. So I'm going to multiply this by 3, this by 3. Okay, when I do, obviously I'm going to get 3. The other one, I'm going to get 7. So my real compound is C3H7. So empirical formula is the lowest ratio of atoms in a compound. You see that? Mm-hmm. So C3H7 would be our final compound there. That's not the actual molecular formula, but we need other information to determine the molecular formula.